This seminar is it's the second part of what we started discussing with Indana last week. So he will focus on hadronic final state for researching the top Squark. So many of you probably already know Nick because he worked with us with GEM, and so actually part of the audience already know him. So he got his PhD in Santa Barbara, now he's in Los Angeles. So we will continue the discussion that we started last week. So yes, we can start.
I don't know. I haven't seen the session last week, so I don't know how we'll continue it, but similar topics. But yes, I'll be talking about top Sqrts, specifically in the hadronic final state. But if you have any questions, feel free to stop me. It's better to do them at the time. Unless if they have to do with the supersymmetric Lagrangian, in which case you can know them to me. But as everyone here probably knows, 2012 was a really big year for particle physics. CMS and Atlas both announced the discovery of the Higgs boson. And this 125 GeV particle was really important. It was like the final missing piece for the standard model. And as you would guess, the current physics, a big part of the current physics programs for both collaborations is to understand this particle's properties and what impact these properties have on the standard model and new physics beyond the standard model. But what I want to talk about today is really just about one property, and that's its mass. And the reason why is 125 GeV is an uncomfortable value. And the reason why is because the Higgs boson is a scalar. It's the only scalar field that we know of. And what this means is that it's extremely sensitive to quantum corrections to its mass. And you can see the formula for the corrections to the mass from a fermion here. And for the most part, we can really just talk about the top quark because the corrections are proportional to the coupling to the Higgs. And you see right here the uppercase lambda, which is basically where we have to say the standard model no longer applies. It's the cutoff value. And without any new physics, all we have is the Planck mass, which is 10 to 19 GeV. And because the Higgs mass is so much lower than the mass of, or the energy of new physics, you have a really weird situation where you have to have a number that's 10 to 38, subtracted from another number that's like 10 to 38, that cancels out in so many 10 to the 34 zeros just to get a 10 to the 4 number. And there's nothing technically wrong with that. It's perfectly mathematically fine. It just seems wrong. There's something missing. And so you might ask, how do you want to solve this? And as a particle physicist, you might be a little selfish and say, well, I want to be employed, so we have to find new particles. But what's something new beyond the Planck scale? Now, the standard tool to deal with this, the standard tool in this toolbox is to propose a new symmetry, something that protects the Higgs mass. And it's not just any symmetry, it's a supersymmetry. And it's a symmetry between bosons and fermions. And so for every particle in the standard model, there's a particle or degree of freedom, however you want to call it, in the supersymmetric particle. And for example, let's have a top quark, which is a fermion. You have a top Sqrt, which is a scalar. Now, these particles have almost the exact same properties except for the spin. But one thing that we do know is that it can't be a perfect symmetry. It must be broken, because otherwise we would have already discovered bottom Sqrts that are 5 GeV. They have to have different masses, which is fine. There's mechanisms to spontaneously break the symmetry without violating it, like the standard model. And what the result of this is that 125 GeV becomes a very comfortable number. That cutoff value, this is the correction now with supersymmetry, and that log is now captured in a friendly. The cutoff is now captured in a friendly logarithm, and now the important factor is the subtraction of the supersymmetric mass against the non-supersymmetric mass. And once again, really only going to be talking about the third generation, specifically top Sqrts, because it has the most important corrections against the large McColl coupling to Higgs. And this is all very subjective. Naturalness is very subjective, and especially it's very model dependent. But a rule of thumb is that as long as the top Sqrk, use both terms interchangeably, is around below around a 1 TeV, we're fine. Like you can accept 1 out of like 1% or even more finely grained corrections. Great. But that's not all. That's not all SUSY can do for you. It's not abnormal to actually impose our parity conservation, which is the conservation of SUSY particle numbers, which means that particles can only be produced in pairs, and that the Lie supersymmetric particle, the LSP, is stable, which is awesome because that means SUSY can naturally provide a dark matter candidate that we can actually produce in applied collisions. And there's of course other pluses of SUSY. And this is very simple rundown, but if you want more information, I have 2 sources I always go to before I make the slides like this because I always forget everything. So if you want more information, go there. So SUSY can solve almost all of our problems, it sounds like. How do we find if that's a possibility? Well, we have to make the particles we can make the particles in a collider and see if we can measure the decays. So what we use is the Large Hadron Collider at CERN near Geneva. So you can see here on the map, and what I'll be talking to you about today is collisions collected by the CMS experiments. Now, the LHC has many different types of collisions. We'll be looking at only the proton-proton collisions, and we've been running for a long time, since 2010. With the last really long run was in 2012, where we had 20 petabarns at 8 TeV. Last year, we pumped up the energy to 13 TeV, but this was not that long of a run. And this year, it's a really long run at the high energy scale. It's still ongoing, but we have, the one I'm going to show you today are the newest results, which are over about 12 petabarns, 13 petabarns of data. Now, CMS, for those of you who aren't aware, I'll do a very, very, very quick and brief overview of it. Its distinguishing feature is the superconducting solenoid magnets, which encases the calorimetry and the tracking systems. And you can see how the CMS is situated. There's the LHC beam, and there's a proton collision. Yellow is the accurate color for proton collisions. Right in the center, you can't see in this diagram, is the inner silicon tracker, which measures charged particle momenta. The blue surrounding that speck is the chromatic calorimeter, which is used to ID photons and electrons and also to measure their energy. And around that, in the tannish blob, is the hadronic calorimeter, which measures the energy of everything else except for muons. And then finally, outside of the magnet is the muon system, which can ID and measure muon momentum in conjunction with the inner tracking system. Now, of course, just to go very quickly over how collisions happen, we have the bunch crossing rate on the LHC is about 40 megahertz, and most of this is not very interesting. So we have sophisticated triggering system, which reduces what we actually prompt to tape to less than a kilohertz. And one thing to really mention here that's kind of interesting and it's not obvious is that we have many, many protons in every collision. So there's actually more than one inelastic collision per event. In fact, there's about 20 extra per event, so which we call pileup. And one part of the reconstruction is to actually identify and remove the contribution of pileup from any of our reconstruction observables. CMS reconstruction is based upon a particle-based reconstruction, and what that means is it uses measurements from all the various subdetectors and combines them down into what we call particles, which have an ID, what most likely is or can be associated to based upon the subdetectors that measured it, and also momentum measurements. So of course you can do things like charge lepton ID by seeing if there's a track that made a track in the muon system, it's most likely a muon, and also if there's a track that also has an ecal cluster, it's most likely an electron. One thing that we use a lot in the analysis I'm going to talk to you about today is particle jets. So these are we're just clustering together those particles into little groups with an algorithm that's supposed to be nearly one-to-one or close to what would happen if a particle jet from a single parton. Now, these jets can also be B-tagged, and that's a term used to identify displaced vertices and tracks that that result from displaced vertices to tag a jet that it's most likely to come from a heavy flavor decay, which will have a displaced vertex. And one of the most important variables we'll be using today is missing transverse energy. So what you do is you take the vector sum of all the particles that you measure and look in the transverse plane, And if there's anything that's not zero, it's not perfectly balanced, then it's pointing to something that's missing, like a neutrino. And its magnitude is commonly referred to as immense. So that's CMS in a nutshell. Now for CMS SUSY searches. SUSY, much more than what I showed you a few slides ago, has a very, very large parameter space and many different models and types of particles to look for. And of course, as a result, CMS has a very diverse SUSY program that spans a lot of this parameter space, but also there's a large overlap between different data analysis looking for the same types of models, which includes looking at the same model but with different lepton channels, as was mentioned, that was talked about last week, but also using different methods and approaches, which is great in the case of discovery. But not a negative, but one takeaway from one result of that is that it'd be impossible to adequately go over the SUSY program in an hour. So instead of a very broad overview of everything, I'll just dive into a single analysis, and then we'll kind of get a bigger picture summary at the end. Like I said before, we'll be looking at only the newest results. These were first announced or released last month at ICHEP, so yeah, it's still pretty new. So as we figure out what type of SUSY model we're going to look for, what type of search we want to go into, we want to bring this back to what we're looking for, which is we're trying to think about the Higgs mass and how can SUSY protect it. So, and also, why not try to solve the dark matter problem at the same time? So we're going to look for SUSY that's or parity conserving, because we want a dark matter candidates. And one of the consequences of this is a new search we look for will have some type of missing energy in the end. And we'll also look at the MSSM, which is the minimal supersymmetric standard model, which is just the least number of particles necessary to satisfy SUSY. Seems reasonable. Now you can decide what type of particles you want to look for, and there's a whole plethora. But once again, we're focusing on naturalists, so let's look at the third generation, specifically top Sqrts, because very strong naturalist bounds. And then you can figure out, well, how do you want to make this particle? Because stops can be made in multiple different ways. And we want to reduce the number of model assumptions as much as we possibly can. It's impossible to completely remove them. But so while the indirect production through gluinos, the supersymmetric partner of the gluon, has a very large cross-section and very nice final states, you have to assume that the gluino is accessible. And it has a small enough mass that we can produce at the collider. Another assumption we're not going to make is that the supersymmetric partners of the left hand and the right hand and top quarks have the same mass, so they don't have to have the same mass. So we're going to assume that only one mass eigenstate to the top Sqrt is accessible to us. And then, now, we already have our model figured out what we want to look for. And one more choice we should probably make, though it has nothing to do with the SUSY model itself, is what lepton channel we want to go for. Now, even though we're looking for the same type of signal, and actually in most of the channels it has the same type of background composition, you need a completely different optimized search design for each targeted lepton channel. And not only that, the background predictions are typically very much different. So it's really nice to focus on just one at a time. Let's go with the all-hadronic. You saw the single lepton last week. It has a 1 plus and it has a larger branching ratio. 46 to 44 doesn't seem that much, but once you factor in the inefficiency of actually identifying leptons, you can't identify every lepton, it's actually a little bit larger, but yeah. So we're going to look for all hadronic stops. Now, what about how does that stop decay after you produce it? Now, how we do this in CMS is that and also Atlas too, is that we interpret the stop decays in simplified models, or SMS. And what this does is, instead of having a very full SUSY model that we try to test, what we do is we focus on a few final states that then can be mapped onto a specific SUSY model in the end. For example, if you have two final states and you say, my SUSY model would have 25% of one, 75% of the other. You can take your acceptances to each final state and map it to your SUSY model in the end. And furthermore, we have two broad categories of these decay modes, and it's based upon the mass splitting between the top Sqrt and the LSP, which in our case is the elasticity curvature. And as you can imagine, as you get more and more compression, your decay characteristics are different. And of course, we further parameterize our signal model based upon the masses of these two particles. We're going to focus on the large mass loading category, and then quickly come back to the more compressed category. Because and the reason why is that the only difference in the search design, the background estimation methods are nearly identical. So we can just, for simplicity, we can come back to it. Now, I have the preliminary result you can look at later if you want some more information. Let's see here, you just Google it. So for the large mass splitting, we can compare two types of decay modes for the top squarks. One is through the top decay, where the stop decays to a top in the neutrino. And the other is the charging node decay, where it decays to a B-port charging node, which then subsequently decays to a W boson in a neutrino. And as you can imagine, these are definitely not exclusive. We interpret it as 100% branching ratio to one or the other, but you can have mixed branching ratios. But instead of adding much more complexity, it's good enough for us to just consider one or the other, because we typically have better sensitivity to this guy, and less to this one. So if it was a mixed branching ratio, it's somewhere in between these two results. And they actually have the very similar final states. The only little difference is the top. So to start building our search, what we're going to do is look at some general signal properties so that we can build a simple baseline analysis. That way we can preserve signal efficiency while getting rid of most of the center model background. And after that, we can see where we are and how we're going to move from there. So here's exploded stop decay, where you can look at. One of the most important characteristics, as I've said before, is that there's missing energy from two LSPs. And this is one of the most important discriminators we have in the center model. And in fact, this is how we actually record the events that we visually analyze. We ask for online triggered events. And for all these cuts, I have the actual selection down here, but it's not really, the actual numbers don't matter too much. It's more what they are. And what's actually quite important is what this missing energy is not. This missing energy is not caused from the typical sources that we see in the center model. For example, a W decaying electronically. So what we can do is that we can identify isolated electrons or muons in the events and beta those events, because they're likely to come from a TD bar decay or W plus jets. Nor are they caused by tau leptons from a W decay that then decay hadronically. So what we do for that is that we reject events with isolated charged particles. And this is much harder to do than in case of electrons and muons, because we don't have the good particle ID. But we do have some tricks to kind of help reduce this background. For example, we require that the transverse mass, which the formula is here, be consistent with the W decay. And I don't know if you guys are familiar with the transverse mass, but if you had two objects, in this case METs and the charged particle, come from the same parent particle, and if the parent particle is fully transverse to the beam, the transverse mass would be at the mass of that particle. As it gets more longitudinal boost, it will be closer to 0. So what you do is you have a cutoff at the parent particle's mass. And finally, the MET we see from SUSY is not from jetness measurement, just jetness measurement. So we can do different types of tricks to reduce this background. But for example, the obvious, of course, is noise killing, which we always do. But also one thing that we do is we reject events where the MET is lined with one of the leading jets in the event, which is typical of multi-jet events where you have really severe jetness emissions. So what else do we have? That's the METs. We also have 6 Sqarks that can actually produce jets. And actually just requiring 5 jets really suppresses Z plus jets and W plus jets events, because it's harder and harder to produce an extra quark. Furthermore, 2 of these are B quarks, which we can select on and even further suppress the Z and W events. And as I mentioned before, we can select B-like jets by looking at if they're suppressants or displaced vertices. And we have 2 working points that we use here of this tagging algorithm. One is a loose working point, which has about 80% efficiency, and we require 2 of those objects. And then we have one that's slightly tighter at 60%. We require one of those to be a little bit more signal, to suppress the background a little bit better. Okay. So that's kind of our baseline, what we're going to start off from. And this is our background composition. The most important background is lost lepton, where we have a W decaying 2 leptons from either TD bar or W plus jet events, or single top 2. where we just don't identify the charged lepton. Either it's too low MTT, or it's just not isolated. We can't pick it out of the background. Following by that, we have Z plus jet sequence, where the Z decays invisibly. Even though we have all these hadronic requirements of jets and B tags, Z likes to make lots and lots of METs, so it has a large cross section, so we still get it. And finally, well, not finally, we have QCD, which is about 5%, which is just multi-jet events that have large MET from severe jetness measurement that does not does not pass any of the cuts from previously mentioned, or heavy flavor decay. And then finally, we have our rare backgrounds, which is about 2%, which is predominantly TT bar Z. So TT bar with associated production of Z boson. And this gets small but still interesting, because when the TT bar decays hadronically and Z invisibly, it's an irreducible background. It looks just like signal. So where does that leave us? After the baseline selection on this data set, we have around 6,000 background events. So actually, compared to what we started out with, it's not that bad. You can get a guess. But looking at one moderately high mass signal event, 800 GeV stop, 100 GeV LSP, we have about 60 signal events. So we actually have quite a bit of work to do. So we go from here is from this baseline, you start to have stricter and stricter selections, so you can at least kill off this background. But one approach that we take here is that instead of having a single very strict selection, what we do is we divide the sample up into subsections that have a gradient S per B that we then interpret on. And this has two effects. One is that you don't actually throw away signal, you still use it if it's a moderately useful search region. But also different signals have different characteristics, right? One might have really hard jets, but low METs. So that way you can target all the different types of signal that we're looking for at the same time. So I'm going to go over how we categorize these events now. One of the most important variables we use is what we call MTB, which comes from the idea that in TT bar, which is one of our most important backgrounds, the W decays leptonically. We have one W that decays leptonically. And if you can figure out where that B is, and you have your MET for the W, the transverse mass should be peaked at the top mass, as I said before. Now, the problem is, though, we have two B-like jets in our decks, and we require at least two B tags. So what we do is we take minimum MT value between those two, which we call the MTB. And what this just guarantees that we do have the cutoff at the top mass. And this is great for signal, because you can see here for a nice signal with large mass splitting is that signal does not have this restraint. There's no, it's just two random LSPs that produce the MET, so it's very broad. But we do want to keep the less than 175 GeV, even though all the background, most of the background is here, because you can see here for signal with low mass splitting, where there's low intrinsic MET, most of this populated down here too. So we can then work on this population indifferently. We can also use top and W reconstruction. And the idea is that signal events have boosted tops and W decays in them, hadronic tops and W decays. And then if we can identify them and tag them, then we can really suppress background, especially Z plus jets and W plus jets. But also TT bar, because remember, TT bar is not, even though it does have one hadronic top in there, it's not as boosted as signal, and also it's only one, signal has two. So you can use it as a discriminator. So when you have a boosted object that decays, it's usually collimated, right? It's boosted. So we do this by first reclustering all the particles in the event into larger, what we call fat jets. And the idea is into one fat jet to collect all of the decays of the boosted, all the decay of the boosted object. And then we do some grooming to remove soft radiation, so it's a cleaner sample, so a cleaner jet, so it is very, very big at this point. And then you can see here for the groomed fat jet mass in TT bar, and then in this top it's QCD. And you see you have two peaks. One is where you have a collimated top, and one where you have a collimated W. And if you want more, there's this CMS released this 2 years ago, maybe 1 year, of this analysis summary, where you can read all about this and other techniques. So it's really useful. But that's not all we can do, not just the mass and our only handle. We can also look for substructure, because remember, this boosted object decayed into 3 quarks at the top. And if you can label that, say, oh, this looks like it came from 3 quarks. You can have further signal suppression versus just a gluon jet, which is just a mesh of energy. So a variable we use for that is called n-subjettiness. Which measures the jet substructure. And n-subjettiness depends on there's tau 1, 2, 3 to infinity, where tau 1 means you're looking to see how compatible your jet is with coming from one single cluster of energy, one energy deposit. Or tau 2 is equal to 3 is 3. And the smaller tau values, the more compatible you are. And I have the formula here, and in the paper I said it has more information, but that's just the general idea. And what we use is the ratio. We use the ratio of hypotheses. So that for top decays, we check for small tau 3 over tau 2, and for W decays, small 2 over tau 1. And I have the cuts here, if you're curious, but we're looking for generally about 200 GeV objects, and then W case and top case 400 GeV. And we divide our sample up into 4 different categories. Of course, in the case of no tops are going to use it for pinpoint anything, because once again, we do want to keep our signal efficiency. But also in the case of no tops, 1 W, 1 top, no Ws, and 1 each. And I'll just quickly go over this, because of course we check everything in signal and data, simulation and data, to make sure we can model and understand it properly. But this is rather important because it's one of the most powerful ways that we can suppress signals, so we should be extra cautious about this variable. So this is the tagging efficiency in TT bar compared to data simulation, and here is the QC, the take rate as measured in QC. And in general, they agree relatively well. There's a small correction for the mistag rate, and we of course apply them when they're needed. Use correction for simulation, but in general, the data and simulation agree moderately well. So furthermore, we have a few more different types of categorization. We break up the signal into 1 or 2 beat tags, once again, to increase signal efficiency. To increase our significance, but then at the expense of efficiency. We break up the event into number of jets. In the case where we can't really reconstruct the top, it's useful for that. And then finally, we force divide the sample up into met bits. And this is great because it gives you a nice gradient of S over higher met, more S over B, less S. And here they are. We have 60 independent search regions. I put this up here because I wanted to use lots of colors on one slide, but you don't need to look at them all. The idea is that we use all 60 together, where we do a bin likelihood fit over all 60 when we analyze the results. So we actually use information from every single piece of this region, which is nice. Now, the one drawback of that is that you need to have precise modeling of the Simon model background in this very complex parameter space. And so to do that, we utilize data-driven background predictions that are defined by these data control regions, which are chematically similar to the search regions that we're trying to predict. So I'll briefly go over that right now. So like I said before, loss lepton is the largest background at 73%. And the data control sample we use is one selected electron or muon. So the idea is that we have our search region, but instead of between a lepton, we ask for one. And the idea is that in our search region, the population is single lepton events where we can't isolate the lepton, and in our control region is where we were able to isolate it. So the rest of the event is actually pretty similar. So it's actually very, very close to our search region, this control region. But then we can apply the full kinematic cuts from for every single search region and get a one-to-one control region to search region with actually slightly more statistics than the search region. And this shows you the met distribution for one such kinematic region. And we do the prediction as so. It's very simple. The number of predicted events is equal to the number of events in our single lepton control region times the ratio of single lepton to 0 lepton in Monte Carlo. So what we do is we allow Monte Carlo to actually handle all of the lepton selection efficiency problems, or to model lepton selection efficiency for us. Otherwise, it's very simple. And of course, our main systematic is our control region statistics. We only get about factor 2 increase with respect to our search region. But of course, we also evaluate systematics on that Monte Carlo ratio to make sure that we can trust it well enough, or at least to put uncertainty on how it would be trusted. Z plus just is slightly more complicated. And the reason why is we have to use 2 data control samples. And in fact, we use simulation to predict the search region, but with these data control samples, we correct the simulation. And we do that for 2 different ways. First is we use the Z plus jets events for the Z decays to 2 charged leptons, either electrons or muons. And the idea is that if the Z decays to neutrinos or to muons, it's the exact same kind of event, right? It's a very, very one-to-one process, so you can use it directly to predict your search region. The negative of that is, of course, the cross-section of to charged leptons that you can tag and to neutrinos. You have like a factor of 3 more statistics in the search region than the control region. So we can't actually go deep into our very, very tight cuts with this data control sample. So instead what we do is we measure a normalization correction to the simulation in our baseline, in a region similar to our baseline selection. So we can measure the correction to our 1B tag and greater than equal to 2B tags regions after large boson PT and also multiple jets. And overall, the normalization corrections are actually they are within the community. They're about 15% uncertainty. So that's how we can get our normalization at the Monte Carlo. But how about the modeling of the rest of the event, the top tagging efficiency? For that, we use photon plus jets. And the idea is that at high boson PT, and by high, I mean we're looking at over 250 GeV bosons, photon plus jets events and Z plus jet events are very much equivalent. They're very, very similar. So from there, we can actually use the photon plus jets to, on top of that, measure the modeling of the boson PT spectrum from 250 GeV to 600 GeV, the number, the top tagging rate, etc. And this is how we put all these 2 pieces of information together. The prediction is equal to the center is equal to just the Monte Carlo, the search region, times a data from Monte Carlo correction measured in the Z dielectron region for normalization, and then a data over Monte Carlo correction from the photon plus jets control region. So once again, it's not too much more complicated, but it is slightly more complicated. Of course, once again, the main systematics are contortion statistics. Quite hard, but then we also evaluate systematics on this translation between gamma plus jets to Z plus jets. Now one slide on the not so important backgrounds. 5% QCD. We do a very similar thing to the other backgrounds, is that we use the data control region. In this case, as I said before, we veto events where in our actual search, we veto events where MET is aligned from the leading jets because this is typical of QCD. Well, if we invert that and require MET to be aligned with one of the leading jets, then we have a QCD enhanced region, as you see here. And then we can once again use simulation to translate these yields, data control region yields, to the search region. And then finally, for the rare processes, which is pretty much just TTZ, we estimate them directly with simulation. And of course, this means that we have to evaluate more simulation-specific uncertainties like the PDF, cross-section, etc. Okay, so that's how we predict the backgrounds. One thing that you might want to add, one thing that we like to do is that even though I feel that these seem reasonable background predictions, you want to have some way to verify that they work before you jump into your search region. So what we do is we have what we call validation regions. These are regions that are similar to our search region, but it's not very high signal contamination. So it can't be actually used for a search region, and also it's independent from all these other control regions I discussed, just so we can test out the methods. And so this is what we do here. We remember our search region cuts is MET 250 GeV. So what we do is we look at a slightly lower 200 to 250 GeV MET region, and then we evaluate all of our search regions. For example, this is one top and one W. And we just test out the methods, just to verify that everything works. And it does. We're quite happy with it. And so it gives us some confidence before jumping into the search regions that these methods are reasonable. And I'm not going to go over with you all these different search regions because it's kind of boring because it's just a bunch of plots like this. This is one example where you see these are different net ranges. This is for 1W, one top, and 1W and one top. Where you see our tidal search right here. But overall, we have good agreement between data and prediction. We have some slight tension, like a very, very minor tension in some of the high net regions, but it's nothing to write home about, nothing significant. So what we do is we just interpret this as a limit on top score. It's a cross section, which I'm showing you right here. So this is the decay where the star decays to a top in a neutralium. And let me explain this plot to you because there's something more like this. And the x-axis is the top Sqrt mass, and the y-axis is the LSP mass. So every point is basically one specific model. So a SUSY model where you have a 600 GB stop and a 200 GB LSP. And the color variance is the upper limit, 95% upper limit on the cross section. And the dotted line is the region, shows you the region where we can exclude it. Where below, within it, with 99% confidence level, we exclude these models. The dotted line, the big dotted line is the expected, what we expect just from our Monte Carlo counts, and the black line is what we observed based upon our the actual data. Now, like I said before, there's some slight tension, nothing significant, so that's why you can, in the high nets top tagged region, so that's why you see that the expected and observed limits are about 1 sigma difference over here. But this is, we're pretty happy with this result. It's, we are at 900 PG stops, which is much stronger than any of the previous results at ATV or even the last year in 2015 run. We got to about 800 GB, so this is actually a large increase in sensitivity.
Can you go back to the one more and show us which bins, one more back, and show us which bins have the small excesses?
We have this one, and then there's one more. This is the QB tag, so there's one more 1B tag in the same bin. So it's just like 1 or 2 events, but it's nothing significant, just
A couple bins at 1 sigma
yeah.
gives you this thing that's a little bit more than 1 sigma.
Yeah, it's cute, but
What's the uncertainty come from there?
the uncertainty on the limit.
No, the biggest uncertainties in those bins that happen.
The data control regions. And
Data.
this up here it's still mostly Z, but it's mostly Z. So it's just the photon control region, and also a little bit also the loss photon control region.
Z is a bigger background than loss photon out there?
At high met, maybe not in this one because you're asking for a W at a top, so maybe then it's still a TD bar. But as you go into higher met, Z becomes more and more important. Yeah, it's nothing significant, but it just happens to be on the same region where the signal is sensitive to. And so that's why you actually don't see it here, right? So this is also this is in the Trajano case where you don't gain from the top tagging, so that's why the expectation and the observation are very much one-on-one. Okay, so that was our dive into the high mass splitting region. Now for a very brief overview of the low mass splitting. Now this is the case where the stop and the LSP are so compressed that neither you can't produce on-shell tops or Ws. There's not kinematically allowed. So what you have are these 4 body decays essentially with LSP and your 3 quarks. Now the background composition is very similar to that of the high mass region, and the search estimation strategy is nearly identical. So we're not going to go over that. We're just going to look over how we design how the search regions were designed differently. And here's another diagram for you. This is now for the 4-body decay. And if it just decays by itself, these events aren't very interesting, right? They're just some soft quarks, right? It's not too much going on. But you can make them interesting if you had an ISR jet, some initial state radiation that boosts the system. The reason why this makes this interesting is because these LSPs typically have some mass, not 0 LSP. So they carry a lot more momentum than the linearly massless quarks. So what you see is you have a different characteristic than you would have in standard model events where you have an initial state radiation. And the search regions are based upon understanding this, or the categorization of the search regions is based upon the properties of this ISR jet. We label it as most likely coming from ISR. And also the decay quarks. For example, we require that that the v-force actually lower PT, because in this case, the v-force has lower PT than its standard model, which might seem counterintuitive to you at first. And here is the result. Now this is the same type of plot as we showed before, except for this little squiggle is way above the other squiggles you saw previously. And once again, the data agrees with expectation, so we did not discover it stops. But the sensitivity of the search was actually quite larger than in the past. So for example, in the past, we'd only be sensitive to 320 G house scores, but now we're up to 420 G. So this type of, we gained quite a bit. All right, so that's my little run into this search. Now let's look at how this fits in with the rest of CMS SUSY program. And once again, this is very brief examples. Don't take it as complete, because it's not even trying to be. So I said before, we have CMS has lots of searches that interpret this model, because these top scores are interesting signal. In fact, here you just see all of them right now. And this line is the one that I just discussed with you. And just to let you know what these mean, the dotted lines is the expected limit, and the solid lines are the observed limits. One I want to highlight with you is the one that Dara talked about last week, which is the searching for the same type of signal, but in a single lepton channel. And that's this guy right here. And what's really cool is that these two searches have completely independent search regions, so you can actually combine them for much more stronger results, which has been done. It's the black line you see here, where you see this is the observed, and this is the expected. And this is actually, I find this quite exciting, because we're finally starting to become sensitive to the 1 TeV top scores in some scenarios. So we're actually being able to start going at the balance of naturalness in some cases. It's fun. But that's not all CMS has. Of course, we look for all types of different types of SUSY. One very brief example is, like I said before, you can make top scores indirectly through gluino decay if you can at least produce the gluino in collisions. And because of the large cross-section, and also because of the amazing final state of having 4 top quarks, I mean, so much fun with that. You're sensitive to much higher mass objects. Remember this, now in this case, this is the gluino mass, not the top score mass. And this model of top score is assumed to be inaccessible, so it's virtual. But you're up to almost 1.8 TeV and gluino, so it's very nice. And of course, we also have many different searches looking for this signal. So yeah, so we haven't found SUSY yet, but it's nothing to be sad about, because the 2060 run is really still ongoing. I mean, the results I showed you about searching just now are about this much data. Right now, we're at this much data, or twice as much, and the run is still ongoing. So yeah, I mean, it should be much more interesting coming up. Especially when I come back to this, is that we're actually finally starting to test the natural top score. And this next analysis on the rest of the data set should be quite fun to look at. That's it.
Looks like your observed limits are systematically to the left of your expected limits.
No, I don't read anything into it. I mean, not all of them, right? Because it's really so
well,
many
on the gluino plot, especially, it looked like they were really systematically.
Maybe a little bit, but no, I wouldn't read anything into it. I mean, you also have to realize that a lot of these searches probably do have overlapping regions too, like the MP2 and the RA2, sorry, H2, the jets missing energy do have overlap, so I'm reading into it.
Question. When you use the photon sample to measure Z background, how do you set uncertainties on photon to Z production ratios and kinematic ratios?
Well, one thing that we do is, I didn't go in this in the talk, is that we don't use photons to directly predict Z, because that's when it starts to get a little fuzzy. What we do is we use the photons to predict differences between data and Monte Carlo, right? So we use it to get a correction. So we don't have to prove that photons can make Z's. What we have to prove is that they have the same data Monte Carlo inconsistencies. which we've checked in more inclusive search regions, more inclusive regions such as this, where this is the, what we like to call is the double, well, the blue line is in photon plus jets, and this is in lots of jets and 1B tab, data over Monte Carlo, and then the color line, I assume this is red, is the same in Z plus jet events. So this is data versus Monte Carlo in both cases. And this right here is what we're trying to test for, is that the data over Monte Carlo ratio is the same in the two processes, which we find is true. And we do apply a systematic map up to 17%.
What's the uncertainty based on? You do it based on the statistics of the red curve there?
This is done from the statistics and the scatter of this ratio.
Isn't that just the statistics of the Z control sample?
It is limited by that, yes. Yes.
How do you gain? I mean, the gain comes from having photon events that have more statistics, right? So if you end up setting limits, uncertainties based on the Z, where are you winning?
Well, because we don't do it in the right because we make the hypothesis that we postulate that they are the same, right? And we look into more inclusive regions to verify that that's the case. It's called, this double ratio is flat statistically in all cases, in all the more inclusive regions. So in a more inclusive region, we measure the systematic. We don't actually go into top tagging with 2B tags, because then you're right, you wouldn't gain anything.
So you take a one-dimensional projection
Yes.
of MET and
And we looked into the other variables too to verify that that's reasonable and it is.
So one question. So when you check your William estimation in the other control region, so basically you have one main control region and you have another one, like it was checked, right? Do you extract some systematic from
No.
this? So you just
This
look
is
at
just a
it.
validation. It's just a sensitivity check to make sure that's, before we open up the box, before we look into the search region.
So you don't take any systematic from
No.
the eventual.
No.
Another question? So if no, we can thank the speaker.
Which is great. The computer came back by itself after the upgrade.
It's just kind of
Yeah, just ignore it and yeah, if it happened overnight, you would never know it happened.
I don't think I'm gonna get too much out of it.
Right.
He works with us regularly.
Yes. Yeah. So probably you can bring it to the lab anyway. But
You might want to copy it, maybe by the lab for copy, whatever. If you, Valdes and I will go there right now and be probably. Meanwhile, will be in the lab. I'll be there until at least 4:30, 4:45 after that.
I mean, if I do this,
so you will be there.
I have a family thing tonight, I don't know if
because I'm just,
probably by 5.
Actually, change the ones that we need to do it's fine for you.
Yeah.
Because usually we do that, so you guys can speak and chat and meet with people around, so you know what you're doing.
But if you could bring him to the lab so he knows where it's at.
Right.
And then you could also get a copy and just. and then
So are you
tomorrow-
free now? Okay, so we will put